Good morning. I want to thank you for the opportunity to participate, even though I can't personally be present. My wife and I were very much looking forward to visiting Buenos Aires, and we hope to do so in the near future. I will tell you that the weather here in Montreal is probably colder and wetter than the weather in Buenos Aires. And I hope that at some point we'll be able to share the adventure that you're going through with your particular meeting. But today, even though I can't be there in person, I'd like to present to you my story and where I believe that we can take young people, the next generation of scientists. And of course, to start this journey, I have to start with an old person, and that would be me. I was actually born the year that Sputnik was launched. And I'm going to assume that maybe only half of you will remember quite when that was. But when I was 2 years old, I traveled from Fort Lauderdale, Florida, up to Athens, Alabama. And Athens was right next to a town called Huntsville, Alabama. And this was in 1960. During that time, the United States had a mission to go to the moon. And the people in Huntsville were the scientists and the engineers who were taking us there. And to be a scientist was one of the ultimate careers when I was growing up. And in fact, I thought that I would be a scientist in space. But as we know, that didn't happen. At the time, scientists were great. They were the good citizens. They were the ones taking care of society, educating, providing improved quality of life. So in 1975, I decided to go to school at the University of Alabama. And when I went, chemistry was a field of innovation, medical breakthroughs, and modern convenience. But when I actually drove the 3-hour drive from Athens, Alabama to Tuscaloosa, Alabama, and became a chemist, something happened. All of a sudden, the chemists and the scientists were evil. We were the bad guys. We were trying to take over the world. We weren't to be trusted. And the question is why? Why did that happen? If we look to this societal image of chemistry, which seems to persist even today as fouling the planet, we don't have to look very far. We look to chemicals. In the 20th century, chemists were responsible for antibiotics and medicines and fertilizers and pesticides and plastics, all of these things to improve the quality of life. We're also responsible for thalidomide, DDT, fluorocarbons, many of the things that had unintended consequences of being endocrine disruptors and bioaccumulating, persistent, and non-biodegradable. Remember that year that I went to college? 1975. Let's look if there's other evidence of this change by looking at the growth in environmental regulation in the United States. I realize this is a little hard to see, but on the y-axis you have number of laws, and on the x-axis you have years. So if we count our first U.S. Environmental Protection Agency law as being in 1870, there was a very, very modest increase all the way up, and I went to school 1975, and that seems to be an inflection point where the number of laws increased exponentially. Why? Well, you can probably trace it back to this book called The Silent Spring, and Rachel Carson putting out a story that really scared people. And in fact, many of these environmental laws are not based on science, they're based on perception. The problem that we found in the chemical industry is that all of the approaches to reducing environmental risk usually focused on reducing exposure. And as you know, reducing exposure is a problem because all of these precautions can fail. And if you fail, you have an accident. So during this time, now let's move forward a little bit to, let's say, the mid-90s. There was a movement going forward called green chemistry. Paul Anastas and John Warner originally framed these concepts sometime in the mid-90s, maybe 98. Green chemistry and engineering focus on the design, development, and implementation of chemical processes and products that reduce or eliminate the use and generation of hazardous substances. It's a great concept. But green chemistry is only part of the story. Chemistry is unique because as a discipline, we create things. We develop new molecules. We often don't know the toxicity or the bioaccumulation, but we invent a lot of molecules. If we want to be sustainable, though, any chemistry is going to have to be done in this era of not only environmental integrity. Everybody seems to be looking at this as green and sustainable, protecting the environment, maintaining biodiversity. All of those are incredibly important. Most of our governments, of course, are only looking at global climate change. I believe that's a mistake. We need to protect more than just the climate. There's also another pillar of sustainability, social responsibility. That is, we have to protect employees. We have to have social cohesion. We can't take advantage of one segment of the world's population to satisfy the needs of another. But there is one part of sustainability that no one in academics really ever wants to talk about, and it's the one that I think could actually enable the rest, and that is the bottom one. You have to make money. If a technology or a product does not make money, there's no way to get it into society. What that means for green chemistry is that green chemistry represents new business opportunities that are sustainable. But we can't make it because the technologies are green and the government's going to regulate it. We have to do this because the technologies are better and people want them and they are sustainable. It is a much harder challenge that we give ourselves. But we have a problem. Industrial adoption of new methods is very difficult. They've already spent millions of dollars for the way they do things today. And so whatever you give them is going to have to not only work, it's going to have to work so much better that they're going to give up the millions of dollars in plant and infrastructure that they've already put in. And this doesn't happen very often. And primarily, you have to look at what industry is looking at. Industry is looking at the next quarter. Can you make money next week? And it gets even worse than that because in a realm of sustainability, people want to get rid of chemicals. So the chemical industry will try to stop you, especially if your innovation will put them out of business. And I only have to refer maybe to Kodak, a company that no longer exists because digital photography eliminated the need for photographic film. Still, if we come back to this idea that maybe we can get technologies in, we're still faced with a problem. How do we prove this viability and significant improvement? And that brings me to really a main topic that I want to bring to you today. I'm an academic. I'm a professor. What do I know about business? And how can I operate a business model inside of a university? I'm going to actually go back to 1871 to a quote by Louis Pasteur. Now this is quite appropriate because he was French and this was originally in French, and of course McGill is in the French-speaking part of Canada. But the quote is very important. There does not exist a category to which one can give the name applied science. There are science and the application of science bound together as the fruit to the tree which bears it, which means we should be able to do incredibly fundamental, groundbreaking research, but we should also be able to utilize the knowledge that's created and translate that into useful things for society. That brings me back to Alabama. George Washington Carver. Now, I can't see you, but I would always ask, how many people know George Washington Carver? If you lived in Alabama, grew up in Alabama, you had to learn about George Washington Carver because it was part of Alabama history. At a time when Alabama was an agricultural-only state, mostly, well, almost 100% based on cotton, there was an infestation of the bug over here on the right called the boll weevil. The boll weevil destroyed the cotton crops. Farmers, society, were starving. What were we going to be able to do? George Washington Carver was a professor at Tuskegee University, just a little bit east of Montgomery, Alabama. In his academic laboratory, he worked directly with the farmers to teach them different crops, better farming habits. In fact, he also taught them better habits to live by. But in addition to that, in his academic laboratory, he started looking at alternative crops. He started looking at products for those crops. He invented and patented hundreds of different products from the peanut and soybeans and sweet potatoes. And that helped develop the markets that the farmers could sell their crops into. Now, McGill disagrees with me because they think peanut butter was invented up here, but I was always taught George Washington Carver invented peanut butter. Imagine a brand new market for that new crop. And think about, can we do this for green chemistry? Well, there's another thing about George Washington Carver. He was a professor. And he had, this is one of his quotes, "Since new developments are the products of a creative mind, we must therefore stimulate and encourage that type of mind in every way possible." In other words, for the young people that we teach, we must help them to be innovative. We must help them to be creative. And we must encourage it and not expect every student to be a faculty member like we are. At the University of Alabama in 1998, I started the Center for Green Manufacturing. This was trying to facilitate bringing science, engineering, and business teams together for new technologies that would be environmentally, economically, and socially sustainable. At the time, it was difficult because no one understood green chemistry in the mid-90s. Most governments told me that I was trying to destroy their economies by eliminating their ability to manufacture. Well, today, of course, we know a little bit different. But in the meantime, we also developed an entrepreneurship program. And I found that students in chemistry had high expectations to be able to change the world. And they expected to do it through developing their own technologies and their own companies. Even when we tried and moved this entrepreneurship into high schools before college, you could tell that the young generation coming up wants to do better than we've done. This is an opportunity for them to do better. And it's not the same as just as being a professor or going to work for industry. It is a major, major career decision. Now, I also backed it up with deeds because I've started a startup company at the University of Alabama called 525 Solutions. And this company will be part of my story as I go through it. But I want to remind you, especially I know a lot of you are professors, a professor can develop not only new knowledge, but new companies, new technologies, and entrepreneurs. You can choose where you're going to make an impact. We've chosen energy, water, materials, and medicine, areas which you can recognize incredibly important today. I'll point out for all the young people in the audience, while everybody is focusing on energy, you should focus your future career on water, because that will be the next critical need that society will have. All right, so let me talk to you a little bit about some of the work that we do trying to implement and put this in action. Please don't try to read this slide, it's very busy, but I want you to notice the iPhone in the middle. The iPhone, by the way, is another technology that had no market, but it completely changed the way society works. I use the iPhone here because you have a platform, which is the iPhone, And then you have apps. And that's how we look at our research. We look at applications for where our knowledge can make a difference in society. Those applications come in a wide variety of different areas, but the platform that we've chosen is a field called ionic liquids. Ionic liquids, many of you may or may not know, but they're very simple materials. They happen to be salts that are liquid at low temperature. They're salts that can be non-flammable, can not burn, can be non-flammable. They can be of a type that don't evaporate. They can be immiscible with water. And they were used a lot as solvents. But there's a mythology that hopefully I'll dispel. So all of you who know about ionic liquids will probably laugh when you recognize this slide, that ionic liquids are toxic, expensive, just an academic curiosity, while at the same time they're green, edible, and biosourced. And if you go to the literature today, you will find papers today that make statements exactly like that. On the other hand, ionic liquids allowed me to open my mind to new perspectives. And that's why I put this quote from Sir William Bragg. The important thing in science is not so much to obtain new facts as to discover new ways of thinking about them. So I'm going to go into green chemistry. And one principle of green chemistry is one that I know is important in South America as it is in the United States and Canada. A raw material or feedstock should be renewable rather than depleting, wherever technically and economically practical. So why would ionic liquids be relevant to this particular principle? Because we found that certain ionic liquids can dissolve trees and grasses and bagasse and just about any biopolymer out there. The major challenge to a carbohydrate economy, or even biofuels or any of the renewable chemicals, is this separation. Lignocellulosic biomass has three major polymeric components. The first is cellulose, and then hemicellulose, and then a horrible aromatic polymer with no defined structure that we generally call lignin. The Department of Energy in the US for years has said if you can do this separation with low energy and low cost, that is the one grand challenge of the carbohydrate economy. Well, how is it done today? Today we use craft processes or organosolv or an alkali process called Alcell. But each one of those processes is a destructive process. They are designed, for example, craft is designed to destroy lignin. And then for your pulp of cellulose, you would then bleach it further to get rid of any traces of the lignin. So you're actually destroying a very valuable polymer. So around 2006 to 2007, we asked a simple question: could ionic liquids dissolve trees? And what we found actually surprised us. The answer was yes. In 2009, we published a paper where we used an ionic liquid, and we used pine, because it's a very popular tree in Alabama, and we were able to, in one step, get a cellulose-rich material and separate lignin. And this had never been done before. It allowed us to set up the idea of a process where you would start at the top with an ionic liquid and possibly a catalyst. You would add the lignocellulosic biomass, in this case pine, to get a solution. And then sequentially you could separate cellulose, hemicellulose, lignin, and then recycle the ionic liquid. So we thought this was great. We thought we had solved the grand challenge that DOE had given to us, and that we could now go after a biorefinery. Of course, not the biorefinery that people talk about today, because almost everybody is just talking about ethanol. So my story about ethanol is that in Alabama, we've known how to make ethanol from corn for hundreds of years. but we drink it. We don't burn it in our car. Instead, you should look at expensive things like essential oils. If you can dissolve orange peel, you can easily get all of the orange oil or sandalwood or anything else. So the strategy becomes any biomass, it doesn't matter which, the ionic liquid, to get a solution from which all of the extractables, I'm just using oil as an example, all of the extractables and chemicals can be separated, the biopolymers can be separated, and now you have essentially almost a chemical factory where nature is providing everything that you need. In getting the orange oil out, again, the process is very simple. Dissolve and distill. All right, so having put that together, we said no one is going to fund us to do this. No company is really going to fund us to do it. So we're going to do it ourselves. Our startup company, 525 Solutions, went to the Department of Energy and we said, we have solved your grand challenge. This is it. And they gave us $100,000 for 6 months to prove the concept, and then we could apply for $1.5 million to actually scale it up. We met every single milestone. It worked perfectly. And we went back with a business plan for phase 2, and we were told ionic liquids are toxic, ionic liquids are too expensive, and phase 2 was rejected. So this was very disappointing because the ionic liquids that we were using were not toxic and they were cheap, but it didn't really matter. There was a mythology, and I think really the bottom line is that chemicals are commodities. They're cheap. Nothing that you do today is going to be competitive with oil unless you can find something radically different. So we thought, okay, we're not going to take this as defeat. We're going to say, we need a better business case. And that made us think, is the ultimate practice of green chemistry elimination of chemistry in the chemical industries? Let's think about this for a moment. One of the major advances that's put under the green chemistry banner is that we take cellulose from nature and we make a monomer of lactic acid from it. And then through chemical manipulation, we take lactic acid and we make a polymer out of it that we then sell to make a water bottle. Now, if you think about why this would be nice for the chemical industry, you can sell the cellulose, you can manufacture the lactic acid, you can sell and manufacture the polylactic acid, and then you can sell a chemical to somebody who's going to make a water bottle. It makes no sense. We have beautiful polymers from nature. Why not just take the polymers from nature and make the water bottle? And that's what I've represented here from an article I published in C&E News in December of last year. Instead of going after fuels and feedstock chemicals, which are dirt cheap, why not prepare new materials which replace the function of the oil-based materials? Now you're talking about higher value. And if you start broadening your scope from cellulose, which seems to be the only focus in the United States, there are lots of other biopolymers. Chitin from crustaceans, cellulose, xylan, and lignin, the xylan and lignin virtually ignored, keratins, collagens. You could actually develop a platform of polymers from nature. And that would lead to new materials, eliminating many, if not all, of the chemical processing steps in between. How can we do that with ionic liquids? Well, the one thing I told you before was that ionic liquids dissolve trees, but what may not have been inherent in that is that the ionic liquids dissolve each individual biopolymer. Cellulose is easily and readily dissolved. Lignin, hemicellulose, and other biopolymers, as I'll show you in a moment. And they are easily reconstituted simply with water or even ethanol into whatever shape that you want. And we've done many For example, we have functional textiles, where we make fibers, where we have added nanoparticles to make them conducting or magnetic. We've made nano-sized cellulose beads that are magnetic with magnetite that allows them to be drug delivery agents. We have made membranes. Now I know the video is not showing here, but essentially we can make a cellulose membrane from cellulose simply by dissolving it, spreading it out, putting water on it. This would have revolutionized the film industry if we still made film, because the filmmaking process requires that you use cellulose acetate. That means you get cellulose, you acetylate it, and then you can process it into film. But the only reason to acetylate the cellulose is to make it soluble so that you can make the films. We no longer need to do that. That allows us, with this ionic liquid platform, to make virtually innumerable products, materials, directly from the biomass. And yes, we are trying to make a water bottle as well without touching nature's polymers. But there's one more. I want to make a business case as I work to finish the talk. And that's another biopolymer which is just now getting a lot more attention, and it's called chitin. I want to point out chitin and chitosan are not the same polymer, although derived from the same source. Chitin, the one that's shown here, is the natural polymer in crustacean shells, and it has these acetylamine groups that distinguish this from, for example, cellulose. Chitosan, they cleave the acetyl groups to leave the amines. And I will tell you that the reason most people use chitosan is because everybody knows chitin is not soluble. But of course, the story has to go on. So let's take a look at how we got started with chitin. Another Alabama story. I don't know how many of you saw Forrest Gump, which the movie is represented down here where they started Bubba Gump Shrimp. But Bayou La Battery is right on the coast of Alabama on the Gulf of Mexico. And in 2010, there was a huge oil spill that shut down the shrimping industry, so we drove down to try and find out how we could help. What we found is that in the processing of shrimp, they take the shell off and they pay $100,000 a month to landfill that biomass. And so we started thinking, why don't we take the chitin? Because chitin has high value. The U.S. market alone for chitin technologies is projected by 2018 to be $63 billion. And yet there's not a single chitin producer in North America. Now when I say chitin producer, I mean in North America, there's not a single company which takes chitin from the crustacean shell so that you can use it. Every chitin user or supplier in North America buys chitin, typically from Asia. And the question is why? Well, the why is because it's an incredibly dirty process and it takes a lot of energy. On the left side, you have the current industrial process for getting chitin from shrimp or other crustacean shells. You start with a shell and then look at high acid and time to get the minerals out. And once you have demineralized the shell, then it's hit with high caustic to get the proteins out. And that leaves you with something you can buy called practical grade chitin. If you want to use it in medicine, which is where high value comes from, you have another purification step, one of which would be using methane sulfonic acid, and you get to pure chitin. There's two things to keep in mind. This is almost exactly like kraft pulping. You are destroying everything around the chitin in order to isolate the chitin, which is never dissolved because they don't know anything that will dissolve it. In addition, the aggressiveness of these steps are such that you clip the polymer. You make it smaller and smaller and smaller as you go. What would happen if you could take crustacean shell, treat it with a single chemical that would dissolve the chitin away from the matrix, and give you a pure, high purity, high molecular weight polymer that no one's ever been able to isolate before. I think it would be pretty important, and of course with our story, this can be done with an ionic liquid. We take the shrimp shell, treat it with the ionic liquid, and we dissolve the chitin. We don't dissolve the calcium carbonate, we don't dissolve all the proteins, but we dissolve the chitin to get a solution to which we add water, and we get ultimately a pure high molecular weight chitin. Okay, back to business case. A pure high molecular weight chitin of a form nobody else has, that has applications in medicine, which are very high value. That looks like a business case that might support this pulping or extraction process. So in fact, we have submitted first to NSF a small business grant to make wound care fibers by combining two important polymers in one fiber product. We also, and this is a bit of a silly one, but you'll be surprised how much of business is actually silly, is the application of ionic liquids towards the extraction of uranium from seawater. And you might ask, what does this have to do with green chemistry? There's actually quite a few points. I won't have time to go through all of them. But I want to point out that if we could mine everything we needed, every metal we needed from the ocean, we could eliminate terrestrial mining. Imagine the impact on the environment, positive impact, if we eliminated mining because we could simply take anything we wanted from the ocean. Well, uranium for the Department of Energy is very important. In the U.S., they believe that nuclear power will be the medium fallback position as we transition from oil to ultimately renewables. And a 100-year supply would be a green, just represented schematically, would be this green box in the upper left. If you look at what is available on land that's known, you've got this much, and I'm going to have a cumulative increase here. If you look at what's undiscovered, you estimate, then you're getting more. And if you look at what's reported in phosphate and shale, if you could recover it all, you'd be getting more. And what's estimated, and then maybe whatever you think might possibly be out there. Ultimately, that's the cumulative 48.5 million tons of uranium possible. How much is in the ocean? That much. In other words, there's an incredible supply, and it's not just uranium, of other metals in the ocean. Now, fortunately, very low concentration, which makes it a challenge to recover. The Department of Energy had a strategy that they were going to take plastic, literally oil-based plastic, they were going to make tons of it with an extractant, and they were going to pull uranium from the ocean. And we said, please don't do that. I don't know if they're going to do it, but I said, do you know what happens when the plastic breaks off and it's not biodegradable, it's going to be in the ocean forever collecting uranium? And they said, don't worry, we'll use Teflon. And I knew that they really did not have a clue. But they were very nice. They funded us with an alternative strategy. That strategy is to take shrimp shell, to extract the chitin. We developed we used our high molecular weight chitin to develop a new electrospinning process, very high surface area. We put the extractant on that, and we have demonstrated extraction of uranium from seawater. So, since no agency in the U.S. would fund an academic to do this work, we went to the DOE and we did a small business grant to develop the chitin sorbents. We won phase one, again, $100,000 for a few months proof of concept. We proved every single concept. We did the electrospinning scale up, we made nanomats, we did the uranium uptake studies, and so we submitted phase two. Now, phase two, we had a problem because we needed a business case, and they assigned somebody to help us. And they said, how much are you going to sell, how much are you going to charge to mine uranium from the ocean? And we said, we're not going to mine uranium from the ocean. And they said, okay, how much are you going to sell your sorbent to people who will mine uranium from the ocean? And of course, we had to say, we don't believe anyone is going to be mining uranium from the ocean except for the government if they decide to go ahead and do it. And so they were very confused by this. But we wrote a different business plan, and we said, look, in the future, you may need this sorbent. If you give us the money to develop it now, we will turn our attention to making product after product after product of chitin that will keep the supply and keep the business running until you need it. Oddly enough, they actually accepted that argument, and so we got $1.5 million to scale up this process. Now, the reason I'm excited about this again is that the process is exactly the same for doing trees, for doing lignocellulosic biomass. And so we are going to be able to now get economy of scale. We're going to be able to show what it would cost to build a big plant. We are going to be able to collect all of the engineering data. So this is facilitating the demonstration of viability that I was talking about at the very beginning. We would not have been able to afford to do this on our own. But the team now includes not only 525 Solutions, it includes the University of Alabama where the sub-award is going, and also it includes now McGill University as we try to move this project forward. But that's not the end of the story. If you followed what I said about George Washington Carver, we cannot have one product. We have to have product after product after product. So we can make tailored biomaterials, combining alginate with chitin. We'll give a high-value bandage fiber. And I showed you that we had won an NSF SBIR for this process, but the processing is very simple. Chitin is soluble along with alginate, and simply combining them in a single ionic liquid solution, you can make a fiber which has the properties of both. And we can do this with virtually any type of biopolymer. The fibers work, we've spun them, and we've actually tested them. I won't take you through the pictures of the actual animal testing on this, but it was very positive. We can also make films for packaging. We can make beads for cosmetics. The list is endless. We have a platform in which we can develop all of these products which ultimately can be used to replace plastics and other type of oil-based chemicals. And we've started another company to try and take advantage of that. And this message is for the young people in the audience. There are non-traditional paths to making a difference in society for chemists and engineers. And you need to think about all of the paths that you might take. Because where people in academics are telling me nonsense things like ionic liquids are both toxic and green, expensive and cheap, and edible and biosourced, we're out there thinking. Because those people who think ionic liquids are toxic or expensive and will never be used in industry gives me a business advantage. Well, alternatively, those people who just think ionic liquids are green and edible and biosourced also give me a business advantage because they're not thinking. I never told you about the ionic liquids are magic. They're magic because they make you think. They allow you to dream. They permit you to consider doing things that others don't think are possible. And by removing those boundaries to the imagination that people with experience tell you not to expect, you can do things which are important. So whether you know about ionic liquids or not, the concept is that a platform for transformational technology doesn't come from what you are using. It comes from how you are thinking. And you must challenge how you think to make a difference. So let me finish with a brief, relatively brief overview of why I'm talking to you from Montreal. I moved in January of 2015 on a quest, a green quest, to become McGill's Canada Excellence Research Chair in Green Chemistry and Green Chemicals. Some people wonder why, because it's awfully cold up here, but it's a beautiful city. It's a multicultural city in the heart of Quebec in Canada, and ironically, the building that they put me in is the old Pulp and Paper Research Institute. They moved out. My office is right here on the corner. It looks a little different today. Well, really not much, just the things around it. They are building a new laboratory space just around the corner from where I am right now here, which will be our scale-up of the facilities. We have new laboratories, new offices, and they are the ones here on the left. And by next year, all of these facilities on the right will be finished as well. This is what the scale up for the biomass deconstruction looks like today, and hopefully soon we'll be able to start building this. The reason I am providing a lot of this information is I do want to tell you that I have a lot of jobs available for people, postdocs, graduate students who want to make a difference in the world today. That's what we're trying to do here. But why Canada? Well, you have to only look at Canada, and this is what I would suggest in whatever country you live. Look at what makes that country run. For economic impact in Canada, pharmaceuticals, fisheries, pulp and paper, agriculture, mining, aerospace materials, we can make an impact in every one of those with a more sustainable technology if we can demonstrate it and get them to listen and try to adopt, or if we start our own companies and put them out of business. In agriculture, this is a $1.6 billion industry. We're making new ionic liquid forms of herbicides which prevent drift and runoff. In drug development, a $7.5 billion potential market, we're making ionic liquids which have new properties of pharmaceuticals. In fishery and agriculture, I just focused on that one and already told you about chitin, but this is a huge market, and Canada has huge fishing industries given the size and nature of the coastline and the various markets. And of course, Canada has a lot of trees. I thought Alabama had a lot of trees, but Canada has a lot of trees, and also agricultural waste, municipal waste. It has a lot of biomass. So one special area I'd like to focus on would be forestry. And what we're trying to do is to develop a discovery center, not necessarily a biorefinery, but a discovery center where we take any biomass, dissolve it in the ionic liquid, and separate the natural polymers, which can be used directly as materials. And then we also get the chemicals, and we look at both chemical and microbial degradation. But the model here is very important. Today, pressure is being put on academics to focus on a single product like ethanol and a single market to replace something that the chemical industry can sell. This is not sustainable. One product. Oil is not sustained on a single product. It's sustained on many products. But the focus that we put on a lot of our academics is also wrong. Replace this chemical so my company can sell that chemical. The focus should be on changing transformational changes. What can you make that would be important? Maybe not today. What could you make that would be important in 10 years? Can we develop the iPhone? Can we develop digital photography instead of trying to make a better film? Unless we allow our students and our faculty to open their minds and discover, once again, we won't know. But I'm not expecting our return on investment to be next quarter. I'm expecting our return on investment to be when society needs it. And most of us can see Society is going to need it relatively soon. So discovery and application of green chemicals and green products from biomass, not to target replacements, but to find innovative new uses where those new uses will eliminate the need for chemicals or chemistry in as much as possible. We've already started. This is our 20-liter reactor. We have developed continuous electrospinning to give us easy recovery of our materials, and we are moving forward. We are going to produce in an academic setting entrepreneurs, companies, and knowledge in the general realm of sustainability. And I don't think we can wait. Now in Canada, I don't know if you're following the presidential election in the United States, but in Canada, I see the social fabric and the intellectual capital and my goodness, all the natural resources that the world needs. I see Canada becoming a leading economy, not by selling its resources, but instead by developing the technology that makes wise use of those resources and providing function to society that eliminates the use for oil, and thus providing economic equality and social justice at the same time. That would be a sustainable economy. So I put these vision statements together. I try not to read both of the statements here, but again, the idea is an academic, professor, students, postdocs. We have to help society. We can't be alone. We need to help inform, to educate. We need to go back to the day when scientists and engineers were seen as the people who were leading society in the right direction, rather than the people who are destroying society. So we have the resources to do that. And I think with the right industrial base we can. But there's one thing to think about. If global climate change is the boll weevil of the next generation, why are we going to wait until climate change has destroyed our economies to start trying to make a difference? Thank you very much for your attention.